first question is, are bounds of the above type always possible for any concept class? Okay, so so essentially the concept class was basically the examples that I showed you. The concept class would be the set of all rectangles, or maybe the set of all half spaces, or maybe the set of all convex polygons. Okay, so those are the concept classes. So are bounds like this possible for all concept classes? The answer is no, only for what are called learnable concept classes. So we'll get to what learnable. So that's the main character of the story. The theory of the learnable is, when is a concept class learnable? That is basically the core question of the learning theory, at least of that particular classic paper. And the second question is, how does epsilon of t comma delta behave, right? So assume it is learnable. How would you want it to behave? Epsilon of t comma delta, as t goes to infinity, you want epsilon to go to 0, right? You have more and more samples, epsilon should go to 0. And for delta, as long as delta greater than 0, that should happen. If you want delta equal to 0, that means that you want 100% guarantees, then you are not going to get anything. So if you want 100% guarantees that you will succeed, you are not going to get it. So generally, you need to have delta to be said to be greater than 0. It can be arbitrarily small. It can be 10 power minus 7. That's fine. 10 power minus 7 probability of failure is achievable, but 0% probability of failure is not achievable. So that's the kind of guarantees that you can get. So more mathematically, you will get forms of this. For a learnable concept class, it behaves as something like v log 1 by delta by t. So as t goes to infinity, you will see that this goes to 0. And you have a log 1 by delta, which is generally not it's very robust. I mean, even if delta is 10 power minus 7, log 1 by delta is going to be just 7, right? So, I mean, say log to the base 10. Delta is 10 power minus 7, it does not look too bad. I mean, you can just as well 10 power minus 7 probability of failure, you can handle by just having 7 times more data points. That's the idea. The real main character here is the V. So V is the measure of a complexity of the concept class. So what do I mean by complexity? So that's the main character of the play here. So if a concept class is too complex, you would have a very high V. If a concept class is simple, you will have a smaller V. So all the definition here comes on what is complex. I mean, intuitively you will understand that the simple complex thing, but the exact definition of V is it requires a class of its own. But I will not be going into too much detail of that. But that's the broad intuition behind it. Okay. So we'll just go a little bit more deeper. Okay. So when is learnability of square, right? So say this is the square. So under what conditions in the training data will you actually be able to learn that square? So what training data would you actually want to see for you to get this? Right. Right. So as long as you have, say, a red point here, so in this area, and this area, and this area, and this area, and you don't even need a blue point by definition, because we always said that take the largest thing. So you don't even need a single blue point, but forget that. So you have, say, a single blue point somewhere here. And as long as you have a red point in this area, just this area, and in this area, and this area, you're going to succeed. So that's basically you don't really care about where red points are occurring here or here or here. You can have it, you cannot have it, it does not matter. So you can actually define success success does not look too hard. If you get enough number of samples, you will get samples in all these 4 areas, and then you are done. So you need to get one sample in one of these areas, each of these areas. That's basically what you want. You will succeed then. Okay, so that's the. So for example, in this case, if you have this, you will. I'm calling success as low error, not 0 error. If you want 0 error, then comes the hard part, right? But if you want 0 error, then what would you need? You would need exactly a sample along this line, and a sample along this line, a sample along this line, and a sample along this line. You would need exactly a sample along those 4 lines, one sample along those 4 lines. So now that is a very rare event, right? I'm having an entire space or entire plane, and I'm saying that I must have a point in that line. So if you are familiar with volumes, you know that a volume or an area of a line is 0. Okay, so because now I'm having uniform things, so it's the probability of me getting a point exactly on that line is 0. But if I add a small width here, Now the area is no longer 0, and there is hope of me getting a point there. So that's where getting the exact answer is hopeless, but approximately getting the answer there is hope. So that's the probably approximately correct part of it. Okay. So now this is the easy example. Okay. So now here, that's what I say. When would ERM work? ERM would work here. So now here we would move on to another example. Okay. So now learnability of polygons. I mean, obviously I gave 3 examples. You would have guessed that one example is going to be negative, so that you would run into a strange issue here. So say learnability of, and now now I'm going here. You would guess that polygons are not going to be able to be learned that, but we'll go into more detail on that. So say assume the data is really on this octagon, and you get only points on the vertices of this octagon. So that's the only points that you get. Actually, there is a line here, but it's too thin for you to see, I think. It's fine. So you don't know that. You don't know in advance that the points are going to lie on the octagon. You don't know that. You are only going to get points. And this is how, points on this vertex, and this vertex are blue, and every other vertex is red. You also don't know that. You don't know that it's an octagon. You don't know that the points on these 3 vertices are blue and everything else is red. You don't know that. But that is the truth. That's the higher level being's view of things. What you do view is samples. So this is what you ideally want your classifier to get. Okay, this is what they essentially say that this area is basically the blue area. This point is the blue area. Everywhere else is red. That's what you ideally want your classifier to get. But is there a hope of a classifier getting it? So we'll settle for the same ERM method that we use. That's basically it picks the largest convex polygon that fits the data. So that's what we will use. Okay. So for simplicity, we'll assume that the data is on the octagon. Okay. So we can have that. We don't know it's on the octagon itself, but we'll assume that the learner knows that data is going to lie on the octagon. Okay. So that means that he does not need to worry about going outside the octagon. So this is what we want. We just have one data point. Can you get this triangle? Is it reasonable to hope that you can get this triangle now with just one data point? No, it's not possible. So you have one more now. So what would, is it now reasonable to hope that you will get, no, also it's not reasonable. Say maybe another data point, you get this. No, also it's not reasonable to hope that you will get this. You get this, no, also it's not reasonable. Here I said it's sample, right? So the same point can repeat. So that's why I'm putting that I'm adding another point here. So here also it's not reasonable to hope that you will get the right answer. So for simplicity, what would the answer look like, right? So what is the octagon? So it's, okay. So at this point, you can hope that even when you have enough samples, now at this point you can hope that, okay, the largest convex polygon that fits the blue data would be this triangle. But you need to have seen all this many samples. You could not have. So when would you have succeeded? You would have succeeded only if you see red points on all the 5 other vertices. If you didn't see even one of the, for example, if you didn't see this vertex, you would predict this to be the blue, because I defined the largest convex polygon. So you know that it's on the other 4 vertices are red. But you don't know if this vertex is red or blue. So because you don't know, you would just predict blue. But once you have that, now you get this. Okay. So you will succeed only if you have red points on all the other vertices. Okay. So octagon, it still looks like it's learnable. Octagon is learnable. Okay. But here's the question: what about polygons? What about decagons? What about a million guns? Okay. So we can have a million. We can have a million-sided polygon. It is possible. And you could have some random 500,000 vertices you pick at random, which are blue. When will you get those exact 500,000 vertices as the right answer? You will get that as the exact right answer only when you see all the 500,000 red points in all the other vertices. Only then you can say that you can get the right answer. And that's where the problem is. The polygon side is not bounded. Doesn't even need to be million gun. It can be billion gun. It can be trillion gun. So I can increase the sides of the polygons, and to get the right answer, I need at least that many samples. And because I don't know the number of sides of the polygon, I need infinite samples. With finite number of samples, I always fail. because I don't know the sides, number of sides of the polygon, I can always fail. So that is the reason where learning polygons is not going to work. Polygons are not learnable. So that's the broad idea. And you should be able to broadly guess that this is a polygon is a far more complex class than a square. In particular, polygons include squares. One rule of the thumb that you can use is how many parameters would you need to describe an element in that class, right? So that would be a good example of a complexity. To represent a square, you just need 4 numbers, right? I mean, you just need to, or a rectangle, you need just 4 numbers. You need the top left and bottom right numbers. I mean, you need the coordinates of the top left and bottom right, and you can represent a rectangle. But a polygon, you would need to represent all the vertices. And if you also want to have the potential to represent a million-sided polygon, that means that you would need 2 million numbers. In fact, even 2 million is probably not enough. Why would you settle for, a million guns are learnable. Polygons are not learnable. That is the key. Even million guns, I'll just wait for a million samples. That's okay. That million is still finite. But polygons are not necessarily restricted to be million-sided. They can be billion-sided, trillion-sided. So that is where you will fail. So it's kind of a very artificial example. I realize that. But this is the only geometry example I can give you which will illustrate easily that you can fail to learn complex classes. If the class is simple, for example, squares or rectangles or half spaces, which you can represent with a finite number of parameters, generally you can learn it. So that's the idea. But this is all intuition. I've not proven anything for you. I will not be able to prove anything because it's too complicated to prove it in this 1.5 hour sessions. But that's the intuition I want you guys to take home. So any questions? So I know this is not particularly easy to grasp. It's a very deep, even in graduate courses, this is generally taught in the second semester of a master's or a PhD course, and this is generally the toughest part of the course. So I don't expect you to fully understand this. It's fine if you don't fully understand it. It's okay, but get the broad idea right. So essentially, if you have classes which are too powerful, too complex, you cannot learn them with finite number of samples. So that's, if you get that level, that's fine. You had a question? Okay. So now we'll get back to that V, right? I mean, we'll try to define the V. Don't be intimidated by the V, but I will try to define the V. So V is basically what is called the VC dimension of H. H is the concept class, which is the set of rectangles or the set of polygons or the set of half spaces. So that's your H. That H is probably not very clear. If you have a fancy H, that's the function class. Okay. So that's V is basically VC dimension of H. So whenever you encounter quantities named after people, you should always be wary because they are named because they are proud of it. So, and it is generally not very easy to grasp, but it's a very elegant concept. So it's one of the most elegant concepts in learning theory, and it has sustained throughout decades. So, but it's reasonably recent. So it's 1989. It was by Vladimir Vapnik. And Alexei Chervonenkis. So Russian mathematicians. It's a very classic paper. It's called on the uniform convergence of empirical estimators to the true estimators. I don't remember the name exactly, but it's a classic paper. And what it does is it takes in a set of, at the highest level, it takes in a set of concepts, like a set of rectangles or a set of polygons or a set of half spaces, and gives a single number at the end of it. It's generally an integer that gives the complexity of that concept class. So before we go there, so we'll just have to define a concept called shattering. Okay. How much time do we have? We can go for now, a little bit more. So a concept class H is said to shatter points x1, x2, xd if for all bit vectors b belonging to plus minus 1 power d. Okay, there exists a h belonging to h such that h of xi is equal to bi. So there's a lot of terms here to unpack. Let's unpack that. Okay, so finally, it's a property which says that you have a set of concepts and you have some points x1 to xd. So for example, you could have a set of rectangles and you could have points maybe this, this, and this. You have 3 points. Okay, so I can say that. I mean, I'm not. It is true, but I'll say that the set of rectangles shatters these 3 points if for all bit vectors in plus minus 1 power d. That means that I can assign a plus 1 or a minus 1 to each of these points. Say maybe I assign 1, minus 1, 1. What's happening here? Plus 1, minus 1, plus 1. So I assign plus 1 to this point, minus 1 to this point, and plus 1 to this point. So this is one bit vector. I have, how many bit vectors do I have for this? Possible, I have 3 points, right? So each point can take either a plus 1 or a minus 1. So it's 2 power 3. So in general, if you have d points, it's 2 power d possible bit vectors. So you choose a bit vector out of the 2 power d bit vectors. For example, plus 1, minus 1, plus 1. And I can get a classifier in this set which labels these points as plus 1, this point as minus 1. For example, here, I can choose, this is possible to shatter, this bit vector is possible to achieve by this rectangle. I can choose this rectangle. If I choose this rectangle will label this point and this point as plus 1 and that point as minus 1. Okay? So that means that this particular bit assignment is achievable by my concept class. So that's just one bit vector. But can I achieve all possible bit vectors? So can I achieve, instead of just plus 1, minus 1, plus 1, I'll also have plus 1, plus 1, plus 1, plus 1, plus 1, minus 1, and so on. All 8 things. Say, I'd say plus 1, plus 1, minus 1. So what would be a rectangle? Can I achieve this pattern? Is that possible? And if so, what rectangle should that be? Does this work? I cover everything. That will say everything is plus 1, plus 1, plus 1. That's not right. If I cover just this, does that work? No, that also does not work. But if I cover this and leave out the minus 1, this would have plus 1, plus 1, minus 1. So that means that I can achieve this bit assignment also. So what it's asking is, for any possible bit assignment, can I get a function, can I get a concept in my concept class that achieves that bit vector? If so, then your concept class H shatters your points D, say x1 to xd. So VC dimension is simply VC dimension of H so VC dimension of H is basically the maximum D such that there exists x1, xd that can be shattered. So that's the definition of VC dimension. And I know it's a lot to unpack, but if you say that you have been to a learning theory session and someone did not say what VC dimension is, I would feel guilty. So you should know that there is such a object which gives you a measure of the complexity of the concept class. So that's the idea. And in the tutorial session, I'll try to just, take it for granted this is the definition of VC dimension of H, and we will try to get the VC dimension of H of, say, rectangles, half spaces, and polygons. We'll try to get that. So if you do for polygons, what is your guess for polygons? VC dimension of set of polygons. What is that? What is your guess? Pardon? Infinite, yes. So VC dimension of polygons will be infinite. So that would mean that this particular statement would be vacuous. You can have v log 1 by delta by t is useless because v would be infinity. So, but for both rectangles and for half spaces, this v would be some small number, which would mean that you are safe. As the number of samples gets higher and higher, your guarantee of error is stronger and stronger. You'll incur lesser and lesser error. That's the idea behind VC dimension. So do you have any questions on this? Yeah. Okay, so we'll move to a different kind of result, which is what you will find very often in online learning algorithms like boosting or Perceptron. We already saw results from boosting. So boosting is an example of already the kind of mistake bound. Essentially, you run an algorithm iteratively. Each iteration you get one new data point, and you bound the total number of mistakes you are going to make. So that's a mistake bound model. So we'll first go with the algorithm first. So there's a very classic algorithm called the Perceptron, which you can prove results in the mistake bound model. So what is the Perceptron algorithm? Algorithm is very simple. So at every iteration, you get one sample, which is you receive an xt in RD. So you receive an xt, which is your instance, and then now you have a current candidate classifier, which is your WT. Which is going to be your current candidate classifier, and you are going to use that to make a prediction on your new instance xt. How do you do that? You just take an inner product. You take wt.xt. So what does that mean? So essentially, you have a half space classifier. Essentially, it's your wt, and if it's on this side of the half space, you predict +1. If not, you predict -1. So that's what you're going to predict. You predict sign of your wt, inner product of your wt and xt, and now you receive your true class of your xt, which is yt. Now you receive that, which is -1 or +1. Now we can see whether you made a mistake or not. Okay, so now if you did not make a mistake, you are happy. So you just keep on continuing, which is what you do here. But if you did make a mistake, you will update your weight vector. So you will update your weight vector wt plus 1 to wt plus yt xt. So if yt is 1, it means that you made a mistake. That means that wt. When would you make a mistake here? Now if you make a mistake, you update wt plus 1 is equal to wt plus yt xt. Right? So you say, for example, yt was +1. Yt was +1. You made a mistake. That means that wt dot xt was actually -1, right? You made a mistake. Only then you update only when you make a mistake. That means that at the tth iteration, you made a mistake on xt. Wt dot xt equal to -1. Sorry, sign of wt dot xt equal to -1. Now you update your wt to wt plus 1, which is wt plus yt was +1, so wt plus 1 becomes wt plus yt xt. Now sign of wt plus 1 dot xt can still be -1. It is possible. There is no doubt about that. But wt plus 1 dot xt is going to be equal to wt dot xt plus xt dot xt. This is a positive number. So that means that wt plus 1 dot xt is it might be positive, in which case it's good. But even if it is negative, it is less negative than wt dot xt. So that means that you are moving in the right direction. So the xt dot xt is always going to be greater than 0, right? So it's a square number, so it's going to be greater than 0. So every time you update, you either make the right prediction every iteration, you either make the right prediction, or when you update, you are less wrong on that instance. So you can keep on doing this. This algorithm is valid in whatever condition. So it's a very popular algorithm. It is valid. But for you to prove something on this, once again, you have to make assumptions. So the assumption that you have to make is there is positive and negative data, and they are separated by a linear hyperplane with margin gamma. By margin, I mean that the distance between the positive data to the separating hyperplane is gamma. And the distance of the positive data from the hyperplane is also gamma. So that means that there is some kind of wiggle room. So even if W star works. If you use W star as your final predictor hyperplane, it works. But even if you had a little bit of wiggle room, instead of W star like this, even if you use something like this, which is close to W star, you would still do well. So that's what this assumption allows you to do. It kind of gets you a zone of values which are correct. And the instances X should be bounded so that they all lie in one sphere so that you can make results. So which means that you have your W star dot xt, there must exist a W star such that yt to W star dot xt is greater than or equal to gamma. And your norm of xt should be, so forget about the norm constraints which are there to just help make life a little bit easier for us in the proofs. So we just have the existence condition. But what we are saying is the perceptron eventually gets the W star. That's what we are actually saying. And that's what we'll try to prove, okay? We can probably wrap it today. So this is an advanced topic, so if you don't get it, it's not a big deal. So it's just get a broad sense of what's happening, and we can close. So if you have any questions, I think we are already close to time. So do you have any questions? How do you apply the perceptron to? What algorithm? Does this answer your question? I mean, the algorithm is here, so how do you apply the perceptron? Is that what you are saying? Just this. So essentially, every iteration you get a sample xt, and you make a prediction, and after that you get the truth. And if your prediction matches the truth, you don't make any changes. You just stay put. But if it disagrees with the truth, then you make a change. That's kind of like how a natural person would learn, right? I mean, if you have some idea of what you're doing and someone says it's correct, you don't do anything. Okay, it's fine. You only learn from mistakes. So if someone says, oh, this is wrong, only then you make corrections. So that's the broad idea. And the update you make is simply you add your, to your current iterate, you add the sample. So I'm assuming yt is always +1, but yt is -1 also, you can handle it. So if yt is +1, you add your wt +1 becomes wt plus xt. If yt is -1, you make wt +1 to be wt minus xt. So that overall your wt +1 dot xt is closer to the truth than wt dot xt. That's the idea. So every time you do that, it happens. That's the. Yeah. So any other questions? There is a multi-class perceptron version of it, and it will have a similar condition also. The condition is not so simple anymore. So it's here. It's linear separability is very easy to see and define, and the margin is also easy to see and define. But for the multi-class also, there is a multi-class perceptron, which has very similar guarantees and very similar assumptions. There is such a thing. So one crucial thing about the perceptron is that there is no distribution assumption. So in all the other cases, you had a distribution assumption. At least for the learnability theory, you made that data was coming from some distribution. So this is a different paradigm from statistical learning theory. So it's statistical learning theory assumes that data is coming from some distribution. But this kind of learning theory, where you don't make that assumption, is often called either online learning or adversarial learning. So essentially, you assume that there's an adversary who is setting the labels. So the standard example that people give here for this is spamming. Right? I mean, the distribution of spam emails, spam or not, is not static. There is no static distribution. So if you build, if Google builds a spam filter which says, oh, lottery means spam, that's what it has detected as the spam classifier, then the spammers will change that. They will no longer put lottery, they will put something else like personal email requiring attention, something like that. So they will put different. So the labels are not coming from a static distribution. The distribution of your truth and your instances changes over time, and it can be adversarial. So they can change the labels to fit your the Google's model, for example. So that's another model of learning, which is called online or adversarial learning. So that's also an interesting. That's a more theoretically grounded, and more results are available in the online learning setting than on the statistical learning setting, because statistical learning is, you don't have very many things under your control, because computer scientists do best when things are adversarial. Okay, you want to prove adversarial things, they are worst case scenarios, they're easy to prove or disprove. But statistical settings are harder to prove or disprove, but that's also a popular setting. So yeah. Do you have any other questions? Yeah, this vacuum thing kind of screwed with us, but it's fine. Anyway, this is an advanced topic, so don't worry too much about it. Yeah.
Is the SVM model based on such notion?
So yeah, so SVM and Perceptron are very, very closely related. So if you see if you work in the primal space, so SVM has both a primal space and a dual space. If you work in the primal algorithm is practically indistinguishable from Perceptron. If you run the algorithm, that's what it would look like. So if you run a stochastic gradient descent on SVM, the primal space, you will get an algorithm which is almost indistinguishable from Perceptron. It's the same.